In this video, we're going to be talking about quadratic functions today. Today, we are going to understand the three main expressions of a quadratic function. We are going to convert between those quadratic forms. We're going to use completion of the square and or vertex information. We already know how to convert one of those conversions, and that's going to be perform one of those conversions, and that's going to be with factoring. Then we're going to solve for x-intercepts or roots of quadratics. It's the same thing, using either factoring and or quadratic formula. We will be using them both, but it would be silly to use them both at the same time. Then we're going to solve application problems that are going to use quadratic machinery. For what it's worth, these problems are going to be a little higher level than what is expected of you in the homework. So if you feel completely lost in the sauce with those, don't fret so much. You'll see there's a rocket problem, and then that one you'll definitely be responsible for. And then there's one involving boxes, which you aren't. I just think it's a really neat problem. So let me sort of give a nice simple graphic here. So we've got the general form of quadratic, which is what we're the most familiar with. And what's really kind of a bummer about the general form of a quadratic is it doesn't really give you any actual information about the quadratic. As a note, remember that quadratics are parabolas, okay? Just as a note, we call this point here the vertex. And if we had the x-axis here, and there's our y-axis, these points right here would be our roots or x-intercepts or solutions in particular contexts. We'll talk about those today. So we've got our general form, and I really like the transformational form because what it gives away is information about the vertex. The vertex is going to have the coordinate pair HK, which is pretty cool. But again, from the general form, in terms of the vertex, we have no idea. We have no idea. So for the vertex, for transformational form, the way that we convert from general to transformational form, we're going to use a technique called completing the square. We're going to complete the square, and that's how we get from general to transformational form. Now, we also have intercept form, which is this guy here. And now this doesn't really tell me a whole lot of information about the vertex. That's not necessarily clear, but the x-intercepts are going to be at the coordinate pairs P, y value obviously has to be 0, Q, y value has to be 0. Now, for x-intercepts, I have no idea necessarily what those are. Well, they're not staring me at the face, given transformational form, and from general form, I certainly have no idea. So just to kind of complete our graphic. So we've got intercept form. The way we get from the general form into the intercept form, if you look at this, you see that all we're going to do here is factor. So in general, for whatever reason, general form is our most popular way to write a quadratic parabola, but it tells us no information. Transformational form tells us a lot about the vertex. It's staring us right in the face. And intercept form, it's the same kind of ilk. The x-intercepts are staring us right in the face. The vertex, there's a little sneaky, trickety trick that you can use from intercept form to get the vertex. And honestly, I think that that's why intercept form is my favorite. Come to my office hour. I'd love to show it to you. It's pretty neat. And it's actually strikingly intuitive. You might be able to figure it out on your own. So we're going to talk about completing the square. So what we're going to do at the beginning of this lesson is we're going to focus on this skill right here. Okay, so let's complete the square. There's a procedure that we're going to need to follow, and I've got, let me write this not as sad. This is my quadratic, and I want to convert this into vertex form. That's another way to say transformation form. Some textbooks will even use standard form. I find that to be tremendously confusing because general and standard both mean pretty much like boilerplate. And so like, oh, this is a quadratic in general form, but here's a quadratic in standard form. And it's like, you know, standard transformational vertex form looks nothing like general form. So, you know, that's just kind of helpful here to use proper language. So transformational form, ultimately, what's going to happen here? After all is said and done, I'm going to have to end up with a quadratic parabola that's going to look like this. X minus h squared plus k. This is the end goal. This is our desired end result. I'm given it like this. I need to convert it to this. Okay, so here's our procedure. Right out of the gate, I'll tell you right now, this a value is going to be the thing I'm going to deal with first. So we're going to factor an a out of the quadratic and the linear terms, not the constant term. If you notice that, we kind of want the constant just hanging out here. So let's factor the a out of those first two terms. So I'm only going to look at these two, and I'm only going to factor a constant out. If you notice, there's no x attached. So I'm going to factor out, so I see 2 and 12. I'm going to go ahead and factor out 2. Ultimately, what I want is the x by itself. So I need to make sure that I'm going to have my x squared alone. Okay. Now I'm going to come up with this magic number, and it's going to feel kind of made up here. But there's something that's happening. I'm going to add and subtract this b over 2 squared inside of the parentheses. So first off, b is going to be my new linear coefficient. And let's compute what this magic number is. I know it's going to feel like this is floating out in space, but that's okay. So let's do 6 over 2 first. I get 3. I'm going to square that. I get 9. Now here's what I'm going to do. I'm going to add and subtract this magic number inside of the parentheses. Why on earth am I doing that? So here's the thing. All I'm doing is taking the quadratic in general form, not changing anything about it, and getting it into transformational form. Effectively, I'm not changing any of the componentry, I'm just changing its aesthetic. So if I'm not changing anything, and I'm just going to start adding something willy-nilly, I also have to subtract that same thing. If I really truly want to do nothing to this thing, what I'm going to go ahead and make sure that I do is add 0. Adding 0 changes nothing. We can add 0 anytime we want. We can multiply by 1 anytime we want. Those things don't do anything. Now, I understand that it looks like we have done nothing, and that's the goal. The goal is for it to look like we've done nothing until we do something. So the third step in our process is kick out the subtraction term using distribution. So this guy right here is actually bad. So what I'm going to do, plus 9 is really cool, but this minus 9 isn't. So what I'm going to do is take the 2, distribute it only to the negative 9. And when I've done that, I've kicked it out, but I distributed the 2 to it. So I didn't actually just kick out this negative 9, I kicked out a negative 18. And now we'll collect up these guys. So the negative 18 and the 14 collect to -4. Now, my final step is I'm going to factor. I'm going to factor this polynomial here. So I'm going to leave this to you all, but when you factor this x squared minus 6x plus 9, what you should get is x minus 3, which goes nicely to x minus 3 squared, which if we look at that, that's what we're looking for here. So now, we've got everything we need and more. We've done it. Okay, we've done our conversion. We see that our a value is 2, we see that our h value is 3, and our k value is -4. We used completing the square to do this. Okay, this is really nice because it's a procedure. So if you practice the procedure, it's kind of like riding a bike, like it never really leaves your brain. Okay, I'm going to show you another way to do this, which requires some formula utility, which is fine. You just have to memorize the formulas. Okay, so just let's take a look at another way to do this. I'm going to choose a slightly grislier problem, one where it'd be more advantageous to use the formula than completion of a square. So there's another way that we can find our information that will help us make the conversion from general to transformational form really quickly. So the thing I want you to keep in mind is this h value isn't just floating out in space. This h value is the x value of the vertex. The way that we communicate the x value of the vertex is through this tiny little formula, -b/2a. So what I'm going to do is take this quadratic polynomial and convert it into general form. So after all is said and done, I'm going to end up with something that looks like this. Okay. Now, right out of the gate, I can tell just by looking at this thing, right? My a is equal to 2, my b is equal to -6, and my c is equal to 7. I can actually just go ahead and say, oh, well, the a value is going to be 2. So we're off to the races already. Boom. Now I'm going to use this formula here for my h value. So remember, it's b, it's negative b/2, and then a, I said was 2. So these negatives cancel. So I end up with 6/4, which comes out to 3/2. All right, so now that's my h value. So what I get to do now is pop that h value in. So you see, we're completing the square without completing the square. So now I need to find the k value. What is the k value again? Well, let's remember something. The vertex of a quadratic parabola is going to have the coordinates hk. So look, here's the k, here's the k. So what this k is the y value of the vertex. I already know this is the x value of the vertex, so now all I have to do is plug the h value into my original function and see what y value comes out. Okay, so let's do that. So I've got f of 3/2. So I get 2 3/2 squared minus 6 times 3/2 plus 7. And so what this comes out to is 2 times 9/4. The 6 and the 2 are going to cancel, so that's just going to change to a 3 minus 9 plus 7. The 2 reduces that 4 to a 2, and so I end up with 9/2 minus 9 plus 7. And so you could think of this 9 as 9/1 and 7/1. And so we need to collect like terms. So we're going to need to do a little bit of fraction manipulation here. If you don't mind, I'm going to leave that to you just so that this video doesn't stretch on for too long. And after all is said and done, I end up with 5/2. Now, what does this 5/2 mean? Well, the 5/2 is the coordinate, the y coordinate of the vertex. So if I think about my vertex, I know my vertex coordinates is 3/2 and then 5/2. And by third, what I mean is halves, because numbers are hard and I'm not smart. So this 5/2, that's the y value of my vertex. So that's it. We're done. We completed the square without completing the square. And I'll tell you now, completing the square for this problem wouldn't be fun because you'd be addressing a lot of fractions. So whichever way you choose to do it is completely fine. Something I want to just really drive home. There's a lot of students, myself, I was one of these included. I used to think I was really, really good at formulas because it felt like it wasn't as thoughtful as, say, an algorithm. Now, the problem with me was I wasn't great at memorizing things. So I would say, oh, no, I'm just really good with formulas. And then I'd get to the test, and I'd look at the test, and I'd go, oh, no, and I would forget the formulas. So ultimately, what I want you to do is discern your strength and say, oh, no, I'm really good at formula memorization. Awesome. Then this method is going to be fantastic. Some of you are going to say, I'm actually really bad at formula memorization. I'm really better with like algorithms, with processes. Okay, well then you're going to want to use completion of the square. Okay. In general, with all things mathematics, what you're going to end up having is a choice between two sort of algorithms. One that works all of the time and is pretty not elegant, and one that doesn't work all the time but is really fancy. In this one, both of these are going to work all the time. It's really just a question of, and frankly, both of them are pretty not elegant. But your choice for what you use has everything to do with just what you believe your mathematical skill set is. Now we're going to find the vertical and horizontal intercepts of this particular quadratic. Go ahead and pause the video and try this one on your own first. Just as a reminder, the vertical intercept is your y-intercept, and that's going to happen when x equals 0. And the horizontal intercept, that's your x-intercept, and that's going to happen when your y or f of x is 0. Okay. Go ahead and pause the video and try these on your own first. All right, let's begin with the y-intercept first. So for the y-intercept, what we're ultimately going to want here is a coordinate pair, and what I already know is that x is equal to 0. So since I know that x is equal to 0, I'm just going to go ahead and plug 0 in for x into my quadratic. So this knocks out, this knocks out. I just have -2. That's great. So okay, there's my y-intercept, my vertical intercept, if you will. I prefer if you wouldn't, I don't like that language. So now we've got the x-intercepts. Now, if you notice, I said x-intercepts. There might be more than one. If we think about a quadratic, how many ways can I make this thing touch the x-axis? Well, certainly, I can make it not touch the x-axis, boom. So there's no reason there has to be x-intercepts. I could also make this thing only touch the x-axis once. If I just make the vertex sort of rest on top of it, it only touches once. That's pretty cool. And if I want to make this thing touch twice, well, all I got to do is just crank the x-axis up here. I can't make it touch more than 3 times. So let's set this up, giving ourselves the maximum possibility here. Maybe there's 2 x-intercepts. There's no reason to believe there would be, but there might be. So our y values are going to be 0. I need my x coordinates now. So now, this thing comes out to be 0 when the y value is 0. So what I have is 0 is equal to 3x squared plus 5x minus 2. Now, the first thing I'm always going to try in solving this equation, since it already equals 0, this is fantastic. What I can do here is either factor or use quadratic formula. We'll talk about quadratic formula later. So I'm going to try factoring, and I'm going to use just the method of factoring that I use. Okay, there's so many methods out there, and there's like cute names for a bunch of them. Me personally, I really like just using grouping in a fancy way. So I multiply the a and the c value. As a reminder, our general form of this quadratic is ax squared plus bx plus c. So I multiply the a and the c value. So 3 times -2, I get -6. And I'm looking for magic numbers. And what these magic numbers should do is multiply to -6 and add to 5. So I'm going to think about these for a second. Oh, got them. -1 and 6. So now I've got 0 equals 3x squared. What I'm going to do now is take that 5x and, ungroup like terms based on what I found my magic numbers to be. And now I'm going to use grouping. Now that I have 4 terms, I can use grouping. So I'm going to go ahead and pop an x out. I get 3x minus 1. Over here, I get 6x minus 2. I'm going to go ahead and pop a 2 out. And since these are the same, I'm going to factor out the 3x minus 1. And I've got an x plus 2. And this equals 0. So here's what I've got. I've got 2 numbers. I've got this one here and this one here. They both multiply together, which is what's happening in the middle here. And they're going to give me 0. I'm going to use what's called the zero product property here, which tells me that at least one of these numbers has to be equal to 0. So I'm going to solve this equation first, 3x minus 1 equals 0. I'm going to leave that to you for right now, and I'm going to get x is equal to 1/3. All right, cool. So there's one of my x-intercepts. And then this little equation here, x plus 2, I'm going to leave that to you all. And I get x is equal to -2. So here are my x-intercepts. So in my solution set, I should make sure that this coordinate pair is present and these two are present. Okay, if this is a little confusing to you, rest assured we are not done with this today. Now let's just find the horizontal intercepts of this quadratic. Okay, let's just find the horizontal intercepts of this quadratic. Again, horizontal intercepts, this is where our y is equal to 0. That's our x-intercept. Okay. All right, go ahead and pause the video and try this one on your end. All right, so as we saw in the last one, we're saying the y value is equal to 0. So I'm looking for coordinate pairs. At most, I'm going to have 2. There's no guarantee I have any. And I may only have 1, but whatever. We're going to have at most 2. I know the y values are going to be 0. That's fantastic. So we're already halfway there to our solution if we think about them as coordinate pairs. So now I'm going to set this thing equal to 0 because that's what my y value is designated to be. So now I'm going to try and factor. So 2 times -4, I'm going to get -8. And I'm looking for things that multiply to -8 that add up to 4. So let's say, okay, well, like, I don't know, -4 and 2, like that multiplies to -8, but those don't add up to 4, so that's not going to work. Okay, well, let's say like -6 or let's say +6 and -2. Those add up to 4, but they don't multiply to -8, so that's not going to work. So I keep piddling around with numbers, and what I end up finding out is that I have no clue what they are. They are out there. They definitely exist, but I'm telling you that they are not obvious. They are not the types of numbers that normal people would think of. So this isn't going to work. So factoring is just not going to do the trick. We gave it a shot. We gave it the old college try, and we found that it didn't sort out. So what do we do now? Well, there's one thing. So I was talking earlier about the types of algorithms you have in math. You've got the really cool one that's pretty quick, but it doesn't work all the time, versus the one that's kind of clunky and kind of blech, but works every time. We tried the cool one. Believe it or not, factoring is in fact cool. And we see that it's not going to work. So we're going to need to use something completely different. And I'll tell you exactly what that is. It's the quadratic formula. So if you remember, quadratic formula is x equals negative b plus or minus the square root b squared minus 4ac all over 2a. There's argument at times over who came up with this first. Some say the Byzantines, some say the Egyptians were doing this long before them, some say the Greeks, some say the Chinese. There's just, it's a hotbed of argument. But, and I've even noticed like a lot of conflicting resources. So this formula, whoever came up with it, it works. So we think of this as ax squared plus bx plus c. Let's do ourselves a favor and identify our a, b, and c values first. A is 2, b is 4, c is negative 4. All right, so now we're going to go ahead and do our quadratic formula. And we're going to come up with our solutions that way. So I use parentheses very liberally. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Another piece of advice I'd recommend that you do is compute this number separately. So 4 squared minus 4 times 2 times negative 4. I see that this is just going to end up turning to a plus. So 4 squared plus 4 times 2 times 4. I end up with x is negative 4 plus or minus the square root of 48 all over 4, because the 2 times 2 is the 4. Okay, great. Now, here's the thing. This square root of 48, we're going to want to simplify that. If you remember, there's a couple different ways you can go about this. I really like using a factor tree. So what are two numbers that multiply to give me 48? Well, I'll use 3 and 16. 16 breaks down to 4 and 4. Both of the 4s break down to 2 and 2. This is multiplicative, by the way, not addition. And I'm going to look for pairs. So I see that there's a pair of 2s. So that guy goes out front of the radical. And then here's another pair of 2s. So there's another 2 outside of the radical. It's multiplying. And the 3's left over. So that's under the radical. 2 times 2 is 4. Okay. And then I've got my negative 4 plus or minus 4 square root of 3 over 4. Now, what I'm going to do next, just again, like this is the process of sort of like, cleaning up our solution. So I see these 4s, I look at the numerator and I look for a greatest common factor to see if I can reduce the denominator. They both have a 4 in common, so I'm going to factor out the 4. And I get negative 1 plus or minus the square root of 3 over 4. These 4s cancel. That's tremendous. If you need to look up simplifying radicals again, I'm going to have a YouTube video posted into the module for that, just so that you have it so you've got a resource available to you. And now I end up with a fully simplified negative 1 plus or minus the square root of 3. Okay, now here's the thing that you need to remember. You hear me saying often plus or minus. Technically, it's both. They're just yielding different solutions. So what I end up with as my final answer is I've got 2 of them. So I've got my first one, my first root. It's going to be at negative 1, we'll say, plus the square root of 3. Which I don't know what that number is exactly, but I don't need to. This is actually, I do kind of know what it is exactly. This is it exactly. If Lumen or the question in particular is asking you for decimals, then use some judgment as to how you round if there's no convention stated. But if it's looking for exact values, this is as exact as it's going to get. I mean, that is perfect. Whether or not we know necessarily what that number is, like we don't need to. We already do. It's that. All right, and then our second one is going to be -1 minus the square root of 3. Okay. And those are our horizontal intercepts. We've done it. And there's our quadratic formula. That was ugly. So, I realized that I wrote that on the wrong slide. That's a bummer. But you saw the math, so all is well there. Now, what we're going to do next is start to write equations of quadratic functions given their graphs, which is going to be a really helpful tool. So we're going to do this in two different ways. First, I'm going to do this in transformational form. I don't know why I'm really passionate about the S there, but I am. So let's do this in transformational form first. You see that I kind of need to just pop in that y-intercept because the picture didn't show it. The way that our transformational form looks and as a reminder, the vertex is the coordinate pair HK. So identify the vertex. Here's our vertex. Our coordinate pair is 2, 2, which means that my H value is 2. So that's huge. So I've got an H value of 2. And I've got a K value of 2. Why did it do that? There we go. And we've got a K value of 2. So that's great. Now, what's going on with the A value? What is that? So here's the thing. I can tell since this thing opens down, this quadratic was reflected about the x-axis because what a quadratic is supposed to look like, is this like opening up U. Since it's facing down, that tells me that I know it's going to be negative for what it's worth. But I still don't know what the A value is. I still have no clue or concept as to what that is. So here's the way I'm going to go about that. I like using the y-intercept because it's a guaranteed coordinate pair. I'm always going to have a y-intercept. So my x value is 0. Why are we doing subtitles? So my x value is 0, and my y value is -6. So now, remember this is y equals. I'm going to plug in my -6 for my y value. And then I've got my x value was 0. And now, I'm going to go ahead and use order of operations here. So I get -6 is a -2 squared plus 2. So now I get -6. The -2 squared, that comes out to 4. All right, now I'm just going to solve for a. So I'm going to subtract 2. So I get -8 is equal to 4a. Divide both sides by 4, and I get that a is equal to -2. So it's very 2-y. There's a lot of 2's all over the place. So I get my y value is -2. I wrote this in transformational form, which is pretty cool. All right. Now, let's do it a different way. I really like intercept form. I super duper do. So for intercept form, we're looking at the x-intercepts. Now remember, for intercept form, it looks like a, x minus p, x minus q. And what p and q represent are the x values of our x-intercepts. So here, p is equal to 1. Let me do this in a different color. So p is equal to 1. Boom, there's our 1. And then we've got q is equal to 3. All right, cool. So now we've got our 3. Wonderful. Now, again, we're almost there. We just need to solve for this a value. Well, what am I going to use for that? I'm going to go ahead and use a coordinate point. In particular, one that I'm guaranteed to have, my y-intercept. So I get -6 is equal to a, 0 minus 1, 0 minus 3. So I get -6 is a times -1 times -3. So I multiply the -1 and the -3 together, I get 3. So I get -6 is equal to 3a. Divide both sides by 3, and I get a is -2, which makes perfect sense because this thing's opening down, so that led me to believe my a value had to be negative anyway. Saw that from the previous slide. So now, there you go. Now, I understand that this looks really different from this, but they are in fact the same quadratic. Okay, if we foiled this out, distributed the -2, collected up like terms, did the same thing here, foiled these, distributed the -2, collected up the terms, we would get to the exact same quadratic. We would get to that quadratic written in general form, which is, as we see, like while it has a nice aesthetic, I guess, it doesn't actually tell us any real information, so it's not of any substance. All right, go ahead and take a second and try this one on your own. Just as a note, I know that this is really unclear. This is -1, okay? And the y-intercept here is at 1, okay? So what we've got here is -3, 0 as a coordinate pair. We've got -1, 0 as a coordinate pair, and we've got 0, 1 as a coordinate pair, okay? All right, so based solely on this picture, I found that intercept form is the most straightforward one to work with. So I've got a, x minus p, x minus q. So right out of the gate, I see that p is -3. And I've got q is -1. All right, and now that minus -3 and minus -1, that's really just x plus 3 and x plus 1. Now I need my a value. So I'm going to use this coordinate pair here, which tells me that x equals 0 and y equals 1. All right, so y equals 1, x equals 0. So I get 1, 0 plus 3. Well, that's a times 3 times 1, which is really just 3a. Divide both sides by 3. A is 1/3. And that's everything we need and more. Okay. Now let's do a real-world application. So I've got a ball. It's going to be thrown upwards from the top of a 40-foot tall building at a speed of 80 feet per second. The ball's height above the ground is modeled by this particular equation. Okay. I want to know the maximum height of the ball. What does that mean? So the maximum height of the ball, let's think about what that means contextually. So if I think about the graph of this ball, right, it's going to look something like this, the graph of the trajectory, the ball's height. Where is the maximum height going to be? It's going to be right here. What point of this quadratic am I really looking for? This is my vertex. So I want to know what the maximum height of the ball is. If I think about every coordinate pair here, this is time, my input variable, by height. What I'm really asking for here is the maximum height of the ball. I'm asking for the y value of the vertex. That's really what I'm asking for. So we'll go ahead and put our answer for part A down here. All right. Now, what I'm going to do here, instead of completing the square for this big gnarly thing, it's not really that gnarly, but instead of completing the square, I'm just going to go ahead and use my H and K formula from earlier. So A is -16, B is 80, C is 40. So H is negative B over 2A. Okay. Those negatives are going to cancel, and I get 80 over 32, which is going to reduce really nicely to around 2.5. Now, I could write this as 5/2, but whatever. We're just going to be plugging this in anyway, so it's fine to keep this as decimal. It's easier to work with, honestly. So now we've got this unknown y value. That's actually what we're looking for here. So what I'm going to do is I'm going to take this 2.5 and plug this in as my t value. And so I've got f of 2.5. That's -16, 2.5 squared plus 80 times 2.5 plus 40. And I'll leave this to you all to kind of work out on your own, but the number you should come out with is 140. Now keep in mind, we're asking what's the maximum height of the ball. So what that means is our answer should be 140 feet. So the highest that this ball goes up in the air is 140 feet high. All right, now I want to know when the ball hits the ground. So what happens there? So we knew that the maximum height of the ball was 140 feet. That was for A. Now for B, I want to know when it hits the ground. When the ball hits the ground, what am I really saying there? So again, when the ball hits the ground, that would be like here. What I know is my height is 0. So we've got this function here. I'm going to set that equal to 0. And what I'm going to need to do here is solve this. So what I'm going to do is I'm going to try factoring. So the first thing I'm going to do is factor out my -8. That is just a common factor. And now from here, I can ignore the -8 and just pay attention to this. So I'm going to multiply 2 and -5. I get -10. And let's look for numbers that multiply to -10 and add up to b, which is -10. So if I try -10 and 1, that only adds up to -9. That doesn't work. I can't think of what they are. So factoring is not going to work. Bummer. I would have loved for it to, because factoring is nice and quick. But for right now, that's just not the battle that I'm going to fight. So now we're going to use, well, we're not going to, we're forced to use the quadratic formula. If you can hear the crying in the background, that's my son going down to sleep. He's even not excited about using the quadratic formula. So if you're not excited, you and him are spirit animals. All right, so negative b plus or minus the square root of, oh gosh, these numbers are going to be grisly. 4ac all over 2a. All right, so we've got some work to do here. Let's go ahead and start by computing this number separately, just to make our lives easier. I know it doesn't feel like we're doing ourselves a whole lot of favors by doing that at this point, but we end up with 8,960 is this result. So now I'm going to go ahead and reduce 8,960. Just for mathematical solidarity, if I want the exact value here. But here's the thing. Let's think about this. When the ball hits the ground, we're going to be expressing our answer in decimal. So I don't actually need to break this down to find exact value. So guess what? Let's just leave this thing exactly as it is. Let's leave this number as it is. It's not asking us for an exact value, so we don't need to worry about it. Now, if you want to practice this on your own, just to really make sure you get it, you can totally do that. What you should end up with, if you do that, is 2, 2, 2, 2. You should have 4 2's out front and a 7 and a 5 left under the radical. So you should end up with 16 square root of 35. Okay. If you get that, that's wonderful. You're obviously very good at simplifying radicals. That will serve you well. Okay. So now, what I'm just going to go ahead and do here is just compute these separately. All right, so for x1, that's going to be with the plus. We should end up with 5.46 seconds. That's fine. And now for x2, we're going to do the minus. We end up with roughly negative 0.46 seconds. So these are our answers, and we don't need to put any more thought into it, and we can pack up and go home. Wrong. Think about this. 5.46 seconds, that makes perfect sense. After 5 and roughly a half a second, the ball hits the ground. Fine. What is going on here? At negative half of a second, it hits the ground? That's silly. Just because we got an answer, that doesn't mean it's a solution. So this is actually not helpful. This is going to be our answer for part B. Again, since it doesn't tell us we need the exact values, then we are not going to do that. So we are going to say 5.46 seconds. It's really important that you consider your units just so that things don't go crazy. All right, for the last one, I'm just going to go ahead and post the solution involving the box up with all the notes for the course. It's going to involve cutting up a box and finding out how much cardboard is needed. I'm just going to leave that up for you all to peruse at your leisure. It's not an expectation for this course necessarily, but I think it'll be helpful to kind of look at, over time.